Hello. I'm going to explain how to write a program that will produce basically this picture, which is a picture of the Mandelbrot set, which is a subset of the complex plane. Um, so I'm going to go over complex numbers and the definition of the Mandelbrot set. I'm hoping that you'll be able to understand what I'm going to say with basically no background in anything except for the English language is necessary, and also um, a little bit of basic arithmetic, but you don't have to know what the complex numbers are or anything like that. So here, this is me violating copyright, putting Wikipedia into the video, and this is the article on the Mandelbrot set. You can see that it looks like this. And there's some history here about this mathematician named Mandelbrot. He's a little bit controversial. I mean, he invented this picture basically, but there's some debate over whether or not this thing maybe gets more attention than it really deserves. Is it an invention? Is it a discovery? Is it really very important? I don't know, but it sure is pretty. And the thing that makes the Mandelbrot set is just this, which I hope you can see. You might want to switch your video to HD. Um, and it's just this recurrence. So what's happening here is you've got some C. All these numbers are complex numbers, and I'll explain what a complex number is and how you can think of it as just a point in the plane. Um, and what the Mandelbrot set is some points in the plane C, and C gets to go into the Mandelbrot set if C is well behaved under iterating this operation. So initially Z is 0, and then you make a new Z by doing the old Z squared plus C. And two things are possible. It could be that these points just run off to infinity, or it could be that they sort of settle down and hang out around the origin. So if they settle down and hang out around the origin, then they get to be in the Mandelbrot set, and if they run off to infinity, then they don't. And one thing that makes the Mandelbrot set so pretty is that it has these really complex, has really complex edge. Um, all right, so I guess I was going to start with, I'm doing this for my class where we're going to eventually implement a program to do this in C. So in order to illustrate the important ideas without giving the solution away, I'm going to do it in Python, which might be harder or easier, I don't know. But I'm going to go through my solution in Python. But first I'm going to explain some things about the complex numbers. So hopefully this is a little bit familiar. So what makes a number complex is that it involves the square root of -1. So there's this letter I that's always used to denote that, and then a complex number is just a number the form a plus b times I, where a and b are real numbers. So that means they're a part of that one-dimensional spectrum or continuum that we call the real line, or they're just decimal numbers. One thing that is surprising is that complex numbers are closed under the basic arithmetic operations of addition, multiplication, subtraction. Is there four of them, right? Addition, subtraction, multiplication, and division. Anyway, maybe I'm just being insane, but I think that's four. So you can see what happens here. Multiplication, you multiply two of these things and you just, expand this. I know from teaching math that kids now call this foiling. I didn't get that when I was in high school, and there's some older people in the class, so maybe you've never heard that term either, but this is now called foiling. Um, and then if you collect terms here, and you replace this I squared with -1, which is what it's equal to. If you square both sides of this equation, you find out that I is equal to -1. You get, and then you regroup these things like this, you'll see that you can understand the result as another complex number. Fascinating. And the same thing happens if you divide or whatever. So actually right here, and I'm using a program here called Sage, and Sage is just Python but with some extra support added for mathematical things. And what this is saying is that I want a complex number represented with a double precision float, which just means a decimal number represented in the machine with a high degree of accuracy. And another way to think of a complex number is that it's just a pair of real numbers. Instead of writing this out, you could just say a comma b. And that's what's happening here. I'm defining this complex number to be 2, 3, and that just means 2, and the imaginary part is 3. The imaginary part is the thing that's multiplied times I. And here I define another one b, so this is another complex number, and it has real part 1/2, real part negative 1/2, imaginary part 8. And then here are just all the things you can do between those: multiplication, addition, subtraction, and division. And you can see that from the program here that no matter what you do, it's still a complex number. And more is true. There is something geometric going on. Let me bring up the article on the complex plane. Maybe I should just say complex numbers. So you can plot complex numbers in 2 dimensions, and the way you do it is, there's a real part and an imaginary part, and you just make a little dot at the point in the xy plane, which is a comma b. So that's not very complicated, and so that means that arithmetic with complex numbers has a geometric interpretation. And I know you could read this, it would be a lot. Okay, so here's the picture I wanted to see. I don't know if you are familiar with vector addition, but if you add 2 complex numbers, a and b, then what happens is the real parts add and the imaginary parts add separately, and the effect is that adding 2 complex numbers amounts to putting the vector corresponding to the second one at the end of the vector corresponding to the first one. So it may be that you find that impossible to understand, for which I apologize, and it's not really super important. But I made a little demonstration here illustrating some of these things and what's going on with the Mandelbrot set. I'm going to show you the important parts of the geometric features that go along with complex arithmetic. So I'm just defining a complex number to start with. This is z. It has real part 1/2 and it has imaginary part 1/3. So there it is. And yeah, so I printed it out, right? And now I wrote this program to sort of label complex points. You can pause the video and look at it more closely if you want. I'm not going to pay a lot of attention to it. So what I've done here is I've plotted z, and then I've plotted z squared, and then I've plotted z cubed. And you can see they sort of go like this. Here's z, and z squared, and z cubed. And if we did more of these things, you would see that what's happening is it's spiraling toward the origin. And the reason that's happening is, I'm going to show you in a second that when you multiply 2 complex numbers, what it does to the length of the result is the lengths are multiplied. So this one has a certain distance, z has a certain distance from the origin, and the distance of z squared from the origin is the square of that distance. And you can see that it's a little bit shorter in this case, and that makes sense. That's because this number is less than 1, so if you square it, it gets even smaller. So every time you multiply by z here, if you think of the distance from z to the origin as a certain percentage, you're just reducing the length of this vector by that percentage. There's still more to be said though, because we haven't said anything about what's happening with the angle. You can also see that the angle is changing, and there's a regularity to that too, which I'll show you in 1 second. So modulus is a fancy word for the distance from a complex number to the origin, and it's defined as the square root of z times its conjugate. And maybe you don't know what that means. It's on Wikipedia. It's basically just the Euclidean distance formula. So it amounts to, the square root of the x-coordinate squared plus the y-coordinate squared. That's it. It's just the Pythagorean theorem. So the modulus of this z that we're considering is 60%, and so if I'd known that before, I could have said that this distance is 60% of that distance, and this distance is 60% of that distance, and that's what's going to keep happening as you keep raising z to higher and higher powers. And here I just kind of illustrated that numerically. I defined two complex numbers. Here's a, has real part 1.5, complex part 3.2, and b is defined similarly. Who cares what these numbers are? So here is a, and here is b, and here's the modulus of a times b. Remember, that's the distance from the origin. And here's the modulus of a times the modulus of b, which you can see is exactly the same. So what happens when you take a product of two complex numbers is that the length, the distance from the origin, changes in the following way. It becomes the product of the distance from the origin of the original two numbers. This word arg is short for argument, and it's just a fancy word for the angle that the point in the plane makes with the x-axis. And I'll show you, if you'll let me go back to this article on the complex numbers. This letter phi is the argument. So here you have z is some complex number. Phi is just the angle that this vector makes with the x-axis, or what they're calling the real axis. So that's it. And where was I? Right here. So what I'm showing you now is what happens when you multiply two complex numbers. What happens to the angle? So here's a again. I guess, oh no, this is a arg, right? Here's a's argument. And this is in radians, and if you don't remember radians from high school, it's probably not worth going back and reviewing it, but you can if you want to, of course. And here is the argument of b, so this is the angle b makes with the origin in radians. And if you multiply the two, then you get this number. And what I'm showing you here is that when you take a product of two complex numbers, the angle is just the sum of the original two angles, and that's why these two numbers are the same. So the arg of the product is the sum of the args. And in this picture, what's happening is, z makes a certain angle here with the x-axis. And when you go to z squared, we've already talked about what happens with the distance from the origin. But what happens with the angle is that it's just twice the original angle. So every time you multiply by z, you're adding this angle, whatever that angle happens to be. And we know, I guess down here, that, did we ever figure out what arg z is? I don't know, but we can. What is z arg? So that is, it's about 0.6. So this is about 0.6 in radians. And that's all that's happening. I showed you that picture of vector addition. I'm happy just having explained what happens geometrically with multiplication. Addition is just translation. All right, and so what I've done here is I've written this stupid program called Mandelator. And what Mandelator does is it executes the Mandelbrot set recurrence a few times, and the specified number of times, with a default value of 5. And remember that, there's some equation that gets iterated. It's this equation. Initially z is 0, and c is the point you put in to see whether it's in the Mandelbrot set or not. This input c is complex, so it's a point in the complex plane. And I've done this recursively. So the base case of the recursion is when num is 0, and then it just returns this. What it's making is a plot, and this is just an empty plot. And this is just some output. The important thing is that you're getting a new z. This is the new z, is the old z squared plus c. And then you plot that thing, and then attached to that the plot that comes from doing the same thing again with the old z replaced with the new z. Okay, and I just want to show you what happens. Remember, the criterion for being in the Mandelbrot set is that you don't run away. I kind of like this other picture better down here because it has some numbers. You can see this is -2, this is 1, -1, 1. So if you keep doing this Mandelbrot recursion on these points, the question is, do they run away or do they hang around? And so here I've done with the z that we've been. Is this the same z? I don't know. You never know. Okay, so this is what happens to this z that we initially started working with. I guess this is just it. It's 0.5 and then a third. And so look at what happens to the points. They just sort of, walk around for a while, but it's unstable and it starts to explode right about here. And then you keep executing the Mandelbrot recurrence. This is scientific notation. That means that this number is followed by 75 zeros. And eventually the machine just can't take it, and it represents the number as not a number. And here's a picture. Of course you can't show the whole thing, but on a small graph you can see the first few. So 20 is the original, and so the numbers are counting down to show you what happens in the subsequent steps. So it's spiraling away. It goes 20, 19, 18, 17, and then I imagine that it just keeps sort of spiraling away, and you can see that the rate at which it's spiraling away just completely grows out of control. So that's a point that's definitely not in the Mandelbrot set. And what number is it? It's like about a half and about 40%. So here this is a half, and this is about 40% of 1, and you can see that that is a white region, and so that's consistent with this picture, which shows that that point probably is not in the Mandelbrot set. You can see there are little specks, but mostly this region is just totally white. Okay, so let's check out what happens with another number. So let's just reset z to be -1 and this small negative number, and that's a point right about here, and it's supposed to be in the Mandelbrot set. So let's see what happens. So we do a few iterations, and these numbers are not exploding like they did last time. They're staying pretty small. And here's the graph of what happens, and it looks like it's just sort of bouncing back and forth between 2 points, and so my graphics are overwriting themselves, and it makes it hard to see exactly what's happening, but the point is just sort of bouncing back and forth. Okay, and it's in the Mandelbrot set because it doesn't run off to infinity. Here's sort of a dumb one that's in the Mandelbrot set, -1 and 0. You can see that the alternation here is just kind of dumb. It just goes 0, -1, 0, -1. And so here's the picture of that, which is sort of similar to this point that was nearby, isn't it? That's kind of mysterious. So let's consider another number which is not in the Mandelbrot set. It's this complex number with real part -3/2 and imaginary part about a quarter. So here everything's going well, and then but then it starts to really blow up and get out of control. And so remember, these things count down, and it starts with 9. Where is 9? Is 9 in this picture? Yeah, here's 9. So it starts here, and then it goes 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 off the screen. And it goes far away and does these things. So this point is not in the Mandelbrot set. And you can see from the picture also that it's not in the Mandelbrot set. It's -3/2 is going to be right about here, and then it's up a quarter, isn't it? So it's like in this region, which is a white region, so it's not surprising that it's not in the Mandelbrot set. Okay, and this one is really cool. Look, it's just kind of like snaking around and being awesome. It's not stupidly bouncing back and forth. It might settle down and do something like that. I don't know. You can let it run for more times and see. But it's just sort of bouncing around, and this is -1/2 and a quarter. So that is in this region. Minus a half is about here, and a quarter. So it's a point from right there. And you can see that really interesting things happen when you get close to, there's not even really a boundary line. This is like that paradox about the coast of England. It seems like this thing should be demarcated. There should be a line that separates the two, but the closer you get, the more complicated it is. And you can watch these videos on YouTube where you just go down into the thing and it goes on forever. Um, so it challenges our idea of what a line is, or what the difference between two regions looks like, because it's infinitely curvy. And that's about it for this, isn't it? So now let's go to the Python where we implement the solution. And I was just kind of Googling around. I was trying to find how to represent an image in Python, and I found this nice, I don't know if you can see it. It's at matplotlib.org users/image tutorial, and I just got it, I think, from Googling Python image. But so the way Python images work is kind of awesome. Here I'm just copying what is done in the tutorial. I import these modules, and this is a PyLab session. So I'm getting matplotlib and pyplot, and also the image, and numpy is a numerical Python, and it's good for high precision arithmetic and doing matrix operations and basically just applied math. So here I'm reading in using the Python image module, the stinkbug file, which I downloaded. And what's super cool is that it translates that complicated file format into something that's actually comprehensible. What it is these are RGB values, which you might be familiar with. So this first number represents the redness of the corresponding pixel. So each one of these triplets is 1 pixel. And then if you go down to here, that's 1 row of pixels. And then you can see that there's another list that begins here, and together they make a list of rows of pixels, and that's what the image is a list of rows of pixels. So it's this many wide, and it's however many larger lists tall, and each one of these is an RGB value, which is a pixel. So it's gray. When R and G and B are equal, what happens is that it looks gray, and that's why it's a gray image. And you can see there's a way to translate from the matrix now back into the picture. And here's that old stink bug. Look at him. Stink bugs are disgusting. And all right, so that is awesome. And I just wanted to show you, let's say that we wanted to make our own image, which we do. We want to make an image of the Mandelbrot set. So this is super convenient for that, because this is, if we make an array of numbers, then we can just translate them into an image and use that to look at the result of our calculation. It's not very fun to calculate the Mandelbrot set and then not be able to see what you came up with, because the whole point is that it's visually pretty. So this arange function, it's a lot like range. You're probably familiar with, oh, go back. What did I do? I'm dumb. So I think it was actually this. And you're probably familiar with the Python range, right? And but this is different because it's dealing with floating point numbers instead of integers, and this is the step. So this is going from 0 to 1, and the steps are 2%. And it lives inside this module, which is the numpy module, and it's called arange instead of range. And so this is in increments of 2%, going from 0 up to just less than 1. So what I've done here is I'm just experimenting, so I think I'll make some dumb gray image, which is it's going to be like this. So what this is going to be is just a RGB value, and they're going to go from, this is going to be the width of my picture. I'm going to go from 0 to 1 in these steps, and then I'm going to go, actually this could have been range, I'm not sure what I was thinking, And so it's going to be this tall, so it's going to be 50 tall. And oh, I guess there is a point for that, isn't it? Because this is making it gray, and so here it's going just like these numbers, except it's being sort of multiplied times 3. 0, 2%, 4%, 6%, 8%, 10%, etc., 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 etc. So it's making that, and right here you come to the end of a row, and then it begins the next row of the picture. And I just showed you the very top part of it because it's pretty boring, I'm sure you'll believe. And that picture, when you render it, looks like this, and it's just going along, it's sort of the diagonal of the RGB cube, going from 0 up to 1. So 0, 0, 0 is black, 1, 1, 1 is white. And it makes a nice picture. And so now I'm just using the built-in Python complex thing. So I was just playing around with it here to see how it works. Maybe I should make this bigger if I can. So this is how it works, and it's sort of familiar, I guess, from what we were doing before. So this is just CDF, what I was calling CDF in Sage. This is similar, and this is the square of the modulus. So to simplify things in my Mandelbrot solution, I just defined these things black and white. It makes it easier for me to understand. And what I do is I define a width. You don't want to use magic numbers, remember. So, define the width and the height in just one place and then always use those. So this is a canvas. I call it a canvas, but what it is just an image that is 5 pixels wide by 5 pixels high, and every pixel is black. And because I actually add one here, it's 6 by 6, isn't it? Instead of being 5 by 5. So it's 6 by 6. And right now everything is black. So I'm going to go through here, and when I find a point that's in the Mandelbrot set, I'm going to turn it white. And so, is that right? Yeah, that must be right. So the Mandelbrot set is going to be white, and the background is going to be black. And now I'm just sort of playing around. What I want to be able to do is, access these things so I can see if they're in the Mandelbrot set or not. So here I'm playing around just with Python, and these are giving me the coordinates of the pixel, and then here's the pixel. So this is the pixel, which is the first one in the first row, and of course they're all black right now. But if these values are right, I'm going to turn them white. Okay, so now this is going to be a little bit weird if you haven't done calculus period or recently. What I'm doing here is I'm partitioning. Oh my god, how am I ever going to explain this? Maybe I can just explain where these numbers come from. So this is start and stop, and W stands for wide. The reason I'm doing that is because this picture goes from about -2 to 1, and that's where my values of -2 and 1 are coming from. So the start is -2, the stop is +1. Delta x is a little increment. So what I'm doing here is I want there to be width many pixels. And no, what am I? Yeah, that is what I'm saying, isn't it? So this is a continuous interval between -2 and 1, and I want to break it up into pixels. So what I do is I just take its length, which is the big one minus the small one, and divide by the number of pixels. And so now delta x is going to let me sort of jump from pixel to pixel. Let me show the picture again. So if there are, let's say, 5 pixels, then delta 0 will go from here to a fifth, and then from a fifth to 2/5, and then from 2/5 to 3/5, then to 4/5, and to 5/5 will finally be 1. So that's what delta x, delta x in this case would be, how far is this? This is 3 divided by 5, because that's what the width is. And so a delta x jump would jump you 3/5, and 3/5 will eventually take you from -2 to +1. And I'm doing the same thing vertically. So vertically you can see that this picture goes from -1 on the y-axis, or the imaginary axis, up to 1 on the imaginary axis, so that's why I pick those numbers. And now I want height many pixels, so I just take the total length and divide by the number of pixels, and then this will be sort of the jump that I can use to get from pixel to pixel. So in this case, with height being 5, it will be, the total distance is 2, and so delta y is going to be 2/5. So I'll go 2/5, 4/5, is that right? 2/5, 4/5, yeah, that's right. It's a little weird, isn't it? So here's, yeah, anyway. Okay, so what I'm doing with, this is transform point, and this is the input, which I call pointy. What I want to do is, here I have sort of grid-like coordinates that go from, you can imagine it being, one corner of the image to the other corner of the image, but I want those to be the XY coordinates in the plane that I consider for the purposes of working with the Mandelbrot set. So I don't, the points in the plane here that are important are points like -2, comma, a half, so those are the ones that I want to consider, not just the integers between 0 and 5. So transform point just sort of maps this grid that goes from 0 to 5 and from 0 to 5, it maps it onto this grid that goes from -2 to 1 and from -1 to 1. And so this is the map, pointy. These lists, this list is the same as this, except the points have been transformed to be the corresponding coordinates and the Mandelbrot coordinate system. So the original one, 0, 0, goes to -2, -1, which is right here in the lower left corner. And then what happens is these things start going up. So first it goes up the column. So it's going up the column until it gets to 1. So the x-coordinate stays -2, and then it sort of reads up from -1 to +1. So it's going like scanning all those. And then it moves 1 delta x to the right. And you can see the code here. All that's happened is that I'm now calling transform point instead of just having CD there. And now it's going over by 1. So here's maybe the next pixel, and then it goes and reads these regions and decides whether or not that pixel should be in the Mandelbrot set or not. So hopefully it's clear what's happening now. And so what am I doing now? I'm still just playing around with this basic structure. Here's the transformed point, but now I'm turning it into a complex number, and I'm printing it as a complex number. So Python, cheekily likes to use J instead of I for some reason. But, here are these coordinates, but instead of pairs of real numbers, we're denoting them as complex numbers. The thing that makes complex numbers so awesome is a point is a number, and then you do arithmetic with the numbers, and it has geometric meaning. That's why the complex numbers are awesome. But here it is just as, a complex number representation. So what am I doing here? Oh, this is the program, or this returns false or true, and it decides whether or not a given point z is in the Mandelbrot set or not. And so how are you going to decide? We've said that if the point bounces around and stays close to the origin, then it gets to be in the Mandelbrot set. But what you do is you just look for some finite number of steps, and then you say, oh, it stays. But you're not really justified, in concluding that it stays, because what if it takes like 10 million iterations for it to finally go crazy and run off? So you have to decide how long you're going to watch it before you decide it's a goner. And my default here is 10, and we'll probably see in a minute that 10 is, I think it should be higher than 10, but anyway, 10 is reasonable. So the default number of iterations is 10, and so C is the number under consideration, which is the input. I probably should have called this variable C. So, the role C plays in the Mandelbrot set formula is C is the point that's being considered. Here's C, right there. That's C. Is he in the Mandelbrot set or not? I don't know. Let's see. Ha ha. All right. And so Z is initially complex 0. And then you just do, for the specified number of iterations, the Mandelbrot recurrence. So the new Z is the same as the old Z times itself plus C. And then you have to check to see here if it's gone crazy. And when I first did this, here I'm taking, this is the distance from the origin squared. So basically I'm looking to see if it's further than distance 2 from the origin. There are other plausible, probably more efficient things that you could do here. If you believe this picture, then what you really need to, if it's not true that the x value is between -2 and 1, and the y value is between 1 and -1, then you can just see from the picture that it's not in the Mandelbrot set. But what I do instead is just check to see whether its distance from the origin is greater than 2, and then I say that it's not. But that takes a multiplication. It would actually be more efficient to do it the other way. But this stupid thing happens, like we saw in the Sage. You start getting these weird values like NaN and INF. So this happens in Python as well as in Sage. You get these weird things, and then if you ask if NaN is greater than 4, the stupid machine says no, which is a reasonable thing to do, because is a table greater than 4? The question makes no sense. But what happens is once it explodes out to NaN, then this comparison becomes like, is a table greater than 4? And then it says false, even though the answer really should be true. You know what I mean, or something. So you have to check for those cases separately. So you can check to see if the real part is INF or is NaN. So I do that for all 4 possibilities: INF and NaN for the imaginary coordinate and also the real coordinate. And so then if it has exploded, basically it's not in the Mandelbrot set. Otherwise it is. And here I just test it. You've always got to test your program. Programs never work. So I test it with these points for which I know the answer. These are some of the things that I was talking about in the other Sage stuff. So the answer should be true, true, false, false, and it is. More importantly, the thing draws the right picture, which really convinces you that it works. And so here it is. So just do this enumeration thing. Like, this is enumerating all the points in our grid. And then we do the transform. And this Z is going to be the point under consideration. I probably should have called it C. And if it is in the Mandelbrot set, then I change its corresponding pixel to white. So remember, all the entries in the canvas were black by default. This means the Cth row, Dth column, they were all initialized to be black, but if it's in the Mandelbrot set, then I set it equal to white. And so what that will do is draw the Mandelbrot set. And let me do this. Actually, I think I need to go, I've been messing around, so I need to reload all these values. So we'll go here, and here, and here, and here, and there. Okay, and I'm just rerunning all these cells because I've been playing around. Alright, and now we're going to look at the result. There it is, it's the Mandelbrot set. Oh my god, it's more beautiful than I thought it would be. And look how complex its edges are. All that infinite complexity makes your head spin. So obviously that's not much resolution because it's 6 by 6. And so here I've just copied the whole program again, And so it was good that we didn't use magic numbers. We used these constants to represent the height and the width, and now we can just change them in one place and get a little bit more resolution. So I don't want to blow your mind all at once. And the number of iterations, it's by default 10. So let's see what you get with. It's kind of crude, but it clearly looks like the Mandelbrot set. Like if this was on a t-shirt, somebody would say you're wearing a picture of the Mandelbrot set. And you can make it have higher resolution like this. And here you can see it's starting to look a little bit better, but still the edges don't look that great. But the edges start to look a lot better when you up the number of iterations. And now you can see it's really starting to look good and fuzzy the way it's supposed to. And so to draw a really great picture using Python, it takes a while. You could change this to 5,000 by 5,000, but I can't do that because I can't entertain you for the amount of time that it would take for that to run. It would take quite a while. When we do it in C, it'll run a lot faster. But I think that's good enough, isn't it? Let's stop it. I'm going to stop the video.